So basically, shell and tube heat exchanger is used for high pressure application. Shell and tube heat exchanger is a large pressure vessel that contains bundles of tubes. So therefore, there is two main fluid flowing in the shell and tube heat exchanger. One is in the tube and the other one is in the shell. The fluid transfer heat through one medium to another through the walls of Therefore, the shell and tube heat exchanger should have walls which have good thermal conductivity. In this experiment, there are two main flows that we are considering, which is countercurrent flow and co-current flow. Countercurrent flow is when the fluid flows in opposite direction, whereas for the co-current flow, the fluid flows in a parallel direction.
Basically, this is the hot water flow rate and this one is the cold water flow rate. For each of it, first, the hot water flow rate should be kept constant and the cold water flow rate should be changed. Second, the hot water flow rate should be changed and the cold water flow rate should be kept constant.
So, before starting, we have to make sure the valves are open and closed according to the table. Firstly, for counter flow rate, the valve that need to be open is valve 1, 12, 16, 17, and 28. For the valve that need to be closed are valve 15, 18, 27, 29, and 30. Others you just leave alone. For the cold current flow, the valve that need to open is valve 1, 12, 15, 18, and 28. Second, for the valve that need to be closed are valve 16, 17, 27, 29, and 30. Others you just left alone.
So, to find out whether the valve is open or closed, we look at valve 16. In this direction, it means that the valve is open, whereas in that direction, it means that the valve is closed.
So these are the data collected, and then we fix the flow rate of the hot fluid, and then we manipulate the flow rate of the cold fluid. And then now we have to find the mass flow rate of the hot fluid, and then these are the formula. So we get 0.167 kg per second, and then this is the mass flow rate of the cold fluid, which is 0.033 kg per second. And then now we have to find the heat of the hot fluid, which is the mass flow rate of the hot fluid times the specific heat capacity of water, which is 4.185. And then we multiply to the temperature difference between the hot fluid, which is 49.7 minus 48.2. So we get 1.05 kilowatt. And then now we have to find the heat of the cold fluid, which is the mass flow rate of the cold fluid times the specific capacity of water, and delta T cold, which is 52.4 minus 29.1. So we get 0.46 kilowatt. And now we have to find the heat loss. So it's the Q hot minus Q cold, so we get 0.59 kilowatt. So now we have to find the percentage error of Q, so which is Q hot minus Q cold divided by Q cold times 100%. And then our percentage error is 56.19%. And now we have to find the average Q, which is Q hot plus Q cold divided by 2, and we get 0.76 kilowatt. So now we have to find the delta T1, which is TT1 minus TT4. T1 is the hot fluid, the inlet hot fluid, and then TT4 is the outlet cold fluid, which is 49.7 minus 29.1, so we get 20.6 degrees Celsius. And then for delta T2 is TT2 minus TT3, which is the outlet of the hot fluid minus the inlet of the cold fluid, which is 48.2 minus 32.4, which is 15.8 delta degrees Celsius. And now we have to find the log mean temperature difference, so this is the formula. Minus 15.8 divided by the ln 20.6 over 15.8, so we get 18.09 degrees Celsius. And then the outer diameter is 9.53 millimeter, the inner diameter is 7.75 millimeter, and the tube length is 500 millimeter. So now we calculate the outer surface area, which is pi dl. Pi times 0.00953 times 0.5, so we get 0.015 meter squared. And then this is the inner surface area, which is pi times 0.00775 times 0.5, so we get 0.012 meters squared. So now we calculate the average surface area, which is the sum of outer surface area and inner surface area divided by 2, and we get 0.0135 meters squared. And then we have to calculate the overall heat transfer coefficient, and then this is the formula. And then start in the values for Q average, and then average surface area and log mean temperature difference, so we get 3.11 kilowatt per meter square degrees Celsius.
In a nutshell, the heat transfer coefficient in countercurrent flow is more efficient than the co-current flow.
Based on our results, the counter current flow has more flow rate, so it has more heat transfer. The higher the flow rate, the higher the heat transfer. Therefore, the counter current flow is more preferably used in heat transfer. So, last but not least, thanks to Segi University for providing us the lab equipments to proceed our experiment. And don't forget to like, share and subscribe our video. Thank you.